And with that introduction, we'll carry on into the applications for eigenvalues and eigenvectors. Let's introduce it with an example. If I want to solve this equation, x dot equals ax, where x is a vector, I could assume a solution. Now, first of all, you could solve this equation using Laplace transforms like we talked about. But let's show another way. If I assume a solution, a, where a is a vector, e to the lambda t. Well, assume, it's like, how do we know what to assume? Well, that's because we've done this problem before, and that's why we assume this solution. So it's like, that's where that comes from. If I take the derivative of that, wishful thinking, a useful principle, e to the u, where u is lambda t, is e to the u. The derivative of it is e to the u. Constant times the function is the constant times the derivative of the function. And then e to the u, now we got to take the derivative of what's up top. U is lambda t, so the derivative of u with respect to t is lambda. If I substitute all this into this equation here, I got x and I got x dot. Lambda a e to the lambda t on the left equals a, right, little a is a vector, e to the lambda t. Now, bringing everything over to the left-hand side, I've got lambda a e to the lambda t minus a times little a e to the lambda t equals 0, where 0 is a 0 vector. Now here's two things that look the same. If I factor that out, now remember with vectors, I times the vector x equals x. So if I factor out a e to the lambda t, I've got to put an I in here, minus a. And then that equals the 0 vector. So this is my second equation here. So now, if this guy is invertible, this is a matrix. If this matrix is invertible, I can bring it over to the right-hand side. Meaning, I'm going to multiply both sides to solve for x. I got something times x, which is what we're trying to solve for. So I've got lambda I minus a. If I invert it, lambda I minus a, and then a e to the lambda t equals 0. So now I've got something multiplied together equals 0. Well, that something, which we said it was x, is our solution. Well, this is always a solution. X equals 0 is a solution to this equation, but it's not very interesting. So what do we want to know? We want to know what's the interesting solution. What we want is that if this is invertible, this is the identity matrix, and all we're left with is x, and that's x equals 0, and that's not very interesting. What we want is lambda I minus a. We want that to not be invertible. so that we get something interesting. Okay, so if we want this to not be invertible, what did we say last time? The determinant of A, where A is this lambda I minus A, this matrix lambda I minus A, we want this to be equal to 0. Because remember, if it was equal to 0, it's not invertible. And we want that to happen so that we get something interesting here. So we want this determinant to be equal to 0. Now what does that say? If the determinant of this is 0, we want there to be a vector A times x. But normally that when you multiply by A times x, you rotate the vector. So if I started out with x and I multiply by A times x, you rotate and scale the vector. What I want is that there to be some vector v that when I multiply by A, all I do is scale that vector. We want A times v, the eigenvector, to equal lambda times v. So for this, so normally for a vector x, you multiply by A and you get a scaled version and rotated version of x. But for these special vectors v, these eigenvectors, eigen, the German for special, at least that's what we're going to say it is. The special vector v, when I multiply that by A, all it does is scale it. All it does is scale it. And so that we're left with another vector, which is just a scaled version of v. And it's scaled by the eigenvalue lambda, which is a scalar. Okay, so let's do an example. If I've got x dot equals ax, this differential equation, kind of like we had before with the mixing problem and using Laplace transforms to solve, but let's use our friend here, a equals 4163. If I've got a minus lambda I times this eigenvector, whatever it is, and I want that to be equal to 0, we want to find v in the null space of this guy here. So let's figure this out. If I've got 4163 minus lambda times I, well, I is a 2 by 2, and if I multiply by lambda, I get that guy. So this vector here is my lambda, a minus lambda I, times v, and v is v1 and v2, my eigenvector, equals the 0 vector, 0, 0. Okay, so let's do this. 4 minus lambda, one minus 0, 6 minus 0, 3 minus lambda. That guy times the eigenvector v1, v2 equals the 0 matrix. So this guy here is my a minus lambda I. if I look at the determinant of that guy, the determinant of A minus lambda I, and I want to make that equal to 0, well, what is the determinant of this guy? A times C minus A times D minus C times B. So this guy times this guy minus this guy times this guy. 4 minus lambda times 3 minus lambda minus 6 equals 0. So FOIL method here, 12 minus 4 lambda, opposite, inner, minus 3 lambda, last, plus lambda squared minus 6 equals 0. Let's bring together the like terms here. Minus 7 lambda plus lambda squared minus 6. 12 minus 6 is 6. And then I've got lambda squared minus 7 lambda plus 6 equals 0. Okay, that looks like something I can factor. And we got lambda 3 and 2. No, that won't add up to 7, but 6 and 1 will. So lambda, let's say plus, well, minus and a minus. Lambda minus 6, lambda minus 1. And you can check that will work. 6 minus 1 is 7, 6, okay. So this times this is 0, well, this is 0, or this is 0. Well, if this is 0, lambda minus 6 equals 0 means lambda equals 6. Or this is 0, something times something equals 0. This could be 0. Lambda minus 1 equals 0 means lambda equals 1. These guys are my eigenvalues. Now, if I look back here, for lambda equals 6, for lambda equals 6 here, plug in 6 here, see what happens. So 4 minus 6 is minus 2, 1, 6. 3 minus 6 is minus 3. And then my eigenvector here, v1, v2, equals the 0 vector. Now we get two equations, minus 2 v1 plus v2 equals 0, or 6 v1 minus 3 v2 equals 0. Now what'll work here? Well, for example, we got two equations, two unknowns. One and 2 will work. So minus 2 plus 2 equals 0. Notice that either equation is these are not linearly independent. They're linearly dependent. And remember what we said about that is that those linearly dependent do not have a unique solution. In fact, they have many solutions. And one of them here is 1 and 2. Now let's go back for lambda equals 1. So we had lambda equals 6 as one of the eigenvalues, or lambda equals 1 as one of the eigenvalues. If we take that example here, four minus 1 is 3, 1, 6. 3 minus 1 is 2, and then the eigenvector v1, v2 equals the 0 vector. We've got two equations, two unknowns, 3v1 plus v2 equals 0, or 6v1 plus 2v2 equals 0. And here, for example, 1 and minus 3 will work. So 3 minus 3 equals 0. And again, you see that these are not linearly independent. This equation is 2 times this equation. Again, we were trying to make these things not invertible, so we succeeded. So the general solution to our original equation, x dot equals ax. So here's my vector x. It's some scalar c1. Here's my first eigenvalue, 6, e to the lambda t. Here's my first eigenvector, 1, 2, plus c2, because remember the sum of solutions is also a solution. E to the lambda t, the second eigenvalue is 1, and the second eigenvector is 1 minus 3. All right, good luck. Stay safe out there.